Hi folks, Chris McClure. This is going to be the very last section of material that we cover for this course, section 6.9, where we are going to, from a data set, build exponential, logarithmic, and logistic models. Okay, so here we go. The first bit is we're going to be talking about when you construct a scatter plot for the data, what sort of model, what sort of mathematical model is suggested by the shape or the pattern of the data. If you have either one of these two patterns, then an exponential function is suggested. The first one is where the a piece for the function a times b to the x power, where a would be positive and b would be greater than 1. But over here to the right, it would be exponential, where b would be less than 1. Moving on, both of these are logarithmic in nature, using either one of these two. They're really the same equation, the same function, but the one on the left is with b being negative and a is positive, but over here on the right, both a and b are positive. Next one, if you see an S sort of shape where you are horizontal, then it goes up, and then it goes horizontal again, either like this or in the opposite direction, then you're looking at a logistic sort of model. So we're going to talk about looking at a data set and using any one of those three sort of functions. In fact, we're going to do an example from each piece. Let's take a look at this first example. Let's read the problem together. Kathleen is interested in finding a function that explains the growth of cell phone usage in the U.S. She gathers data on the number, in terms of millions, of U.S. cell phone subscribers from 1985 through 2005. The data are shown in Table 9, this table right here. This is also on page 487 of your textbook. We're going to draw a graphing. We're going to draw a graph using a graphing utility. We're going to draw a scatter diagram, that is, with year as the independent variable and the number of cell phone subscribers as the dependent variable. Using the graph utility, we'll fit an exponential function. I'll show you how to do that. Express the function in the form of a is equal to a sub 0, which is some constant, the initial amount for the year 1985, times e to the kt. You're probably wondering, what in the world am I talking about? Well, the calculator is going to give you an equation of the form where you have some number times some other number raised to a power, x. Well, we will do a little bit of algebra to put it in this form right here. We will graph the exponential function found in part B or part C in the scatter diagram, so we could fit our model against our data. Then we will predict the number of U.S. cell phone subscribers for some future year, like in, for example, 2009. And we will interpret the value of k found back here in part C. Let's go ahead, pull out your graphing calculators, and we're going to go ahead and put this data into your, in through your statistics menu to create lists. You're going to want to do one list for the year, and you can let x be equal to 1, correspond to the year 1985, and 2 correspond to 86, and so forth. Okay, like you see here. And that would be for your first list. And your second list will be the number of subscribers in millions. So I'm going to jump out of here real quick. I'm going to pull up my graphing calculator. Here it is. You go into your statistics menu. and you select edit, which is option 1. And I've already taken the liberty of entering this data. So, but to go from one list to the next, to the next, to the next, and so forth, you can just use your arrow buttons. But I've already input the data. For the second problem, I'll show you how to input data, but this was a long example. That's why I went ahead and did it in advance. So in L1 is the year since 1984, with 1 being 1985, 2 being 1986, and so forth. And in the second list here is the number of cell phone subscribers in millions. All right, let's go ahead and plot this. To plot this, you are going to hit the second button, and up here, this first button across the top row where it says stat plot in blue. And then go ahead and select number 1 for the stat plot. You could have several stat plots happening at the same time. We're just going to do stat plot number 1. We're going to turn it on first. So make sure that you left arrow over here to on and hit enter. And by default, this first sort of graph should be displayed, but if you want a line graph or a histogram, then you can choose either one of these. By default, the X list is the list L1, and the Y list is going to be L2. You're probably wondering what L1 and L2 are. Go back to your, statistics menu. Yeah, go back to your statistics menu, hit enter, edit. Well, enter. And L1, L2, L3, ... are the column headers for each of these lists. Also, they're just in the name of these different lists that you see here. If you hit second and go into your list menu, those are really names of lists. L1, L2, L3, L4, ... Okay. So go back into stat plot number 1. So if the X list is not already L1 and Y list is not already L2, then you can go ahead and change it. How can you change it? Like, for example, suppose that we want to change Y list. So make sure that your cursor is down here on Y list. Well, suppose that we want to change that to L3. Now, you could select L3 by looking down here. You see in blue above the 1, 2, 3, 4, 5, 6. These are list names, and you can access them by hitting second, which is the blue, and that number. So you can go ahead. Suppose that we want to do L3. Now let's move it back to L2. We better clear that. Let's go ahead and clear that, and let's try it again. L2. There we go. And we'll enter. And then finally, your marker down here, you can use either one of these 3. And I prefer this first one. We'll leave it there. Now let's go to Window. We're going to let X go from 0 to 25. If you were to go back to the presentation, go back to here, look at the range of values for X. X goes from 1 to 24. So in choosing your range of values, you want X minimum to be just a little bit less than your smallest X value, and X maximum to be just a little bit larger than your largest X value. And then X scale should be chosen so that there's between 5 and 10 tick marks. X scale is just the interval for each tick mark on the x-axis. And then for Y minimum, let's go ahead and take a look at the range of values for Y. Y varies anywhere from just a little above 0 all the way up to a little over 270. So it would be okay for us to let Y vary from 0 to 275. And indeed, that's what I've got right here for y minimum of 0, y max 275. And then 25 would be a good interval for the y tick marks. All right, and then go ahead and hit graph. Now, this is what it should look like. If you happen to have any functions input for y1, y2, y3, and so forth in the equation editor, go ahead and clear them out. Just all you have to do is hit clear. All right, so here's your scatter plot. Going back to the PowerPoint. Now we're going to go ahead and do the exponential regression on the calculator. Now, how do you do exponential regression? I'll show you. Go back to your home screen by going and clicking on second and quit. Go back into your stat menu. Right arrow over to calculate. And then go to option 0 for exponential regression. And hit enter. And then you have the equation y is equal to a times b to the x power, where a is equal to 0.864977535, and b is equal to 1.318554023. You can round these off to maybe 3 or 4 decimal places if you choose. All right, so that's the thing that we've got here. Notice that our R value is close to 1. That means that we have a pretty good fit, meaning that our data really are exponential in nature. And here is the form of our equation right here, where you've got A and B right there. Moving along here. Now, if we wanted to put our equation into this form, a sub 0 times e to the kt, I'll show you how to do it. Now, our existing equation is already in this form, a times b to the x power. And we want to put it in this form here. So I'll show you how to do it. Now, by the way, x is going to be equal to t here. Now, the constant coefficients are going to be the same. The a is going to be the same thing as a sub 0. A sub 0 is the same thing as a. So now we need for b to the x to be the same as e to the kt. By the way, you could write e to the kt as e to the k raised to the t power. And if we really want x to be equal to t, that means that b must be equal to e to the k power. But we already know b, but we don't know what k is. So how do we find b? Well, take natural log of both sides. And we'll see that k is going to be equal to natural log of b. And that's going to be approximately 0.2765. Okay, so now we can go ahead and write our exponential equation, if we so choose, with an exponential base of e, where k is equal to natural log of b. Okay, now if we wanted to, we could go ahead and put that equation into our equation editor. So let's go ahead and do that. Oops, excuse me. I want to pull up my graphing calculator here. There we go. Go in your equation editor and input that function here. And I'm going to pull up my textbook here. And I'm going to go ahead and type in 0.86498. Okay, and then times, you don't really need to put times, but I'm going to, e raised to the 0.2765 0.2765 times x. There we go. And the right arrow to get out of the exponent. And then go ahead and hit graph. And you'll see that it's not going to be an exact fit, but it's pretty close. Could be closer, but it's not too bad of a fit. Going back to the presentation here. For part C of this problem, what is the predicted number of cell phone subscribers in the U.S. in 2009? Well, the year 2009 corresponds to x being equal to, well, 25. Because if you take 2009 minus 84, that's 25. So we will plug in 25. Now, you could do it algebraically by going in your equation, replacing x or t by 25. Now, in your graphing calculator, I'll show you how to do it. You go to your table menu, table setup, and down arrow down to where it says independent, right arrow over to ask, hit enter, and then go over to table, and then type 25 for x and hit enter. And the graphing calculator will evaluate your function, the equation or the function that's in for y1, when x is equal to 25. And that works out to be 869.09. As in, we are predicting that there will be about 869 million subscribers, cell phone subscribers in the U.S. in the year 2009. What does k mean here? When you have this function right here, a sub 0 times e to the kt, what does k mean? What is the 0.2765? How do you interpret that? Well, this value for k represents the growth rate of the number of cell phone subscribers in the U.S. Annual rate of 27.65%. That's the same as 0.2765 expressed as a percentage, with a continuous compounding. We don't normally think about cell phone subscribers' rate of growth as being continuously compounded, but it works just as well with subscribers as for money. But understand, though, that this is not going to be a sustainable model, this exponential model, because, you know, the number of subscribers will eventually level out. And as a matter of fact, as we are pointing out in E, the previous part, is that the number of people in the United States, the population of the United States, is only a little over 300 million. Certainly well below the predicted number of subscribers. So that right there just points out the problem here is with exponential growth. So the actual number of cell phone subscribers will have to level out to where it's just below the total U.S. population. We understand that not every U.S. citizen will own a cell phone. So, for example, small children will not have a cell phone subscription, or prisoners in state or federal prisons will not have cell phone subscriptions. At least they shouldn't, for example. So the number of cell phone subscriptions will always be less than the total U.S. population. So anyway, moving along here. Logarithmic models. Let's go ahead and read the setup here. Jody, a meteorologist, is interested in finding a function that explains the relation between the height of a weather balloon in terms of kilometers and the atmospheric pressure measured in millimeters of mercury on the balloon. So we want to find the relationship between height and pressure. She's going to collect the data shown in table 10. And this is the data right here. And this is actually what we're going to put in together in the calculator. We're going to draw a scatter plot. We're going to fit a logarithmic function to the data. We're going to draw that function on top of the scatter plot. And we're going to make a prediction. So let's go ahead and pull our graphing calculators again. And I'm going to go into your stat menu and edit. Now I'm going to go into list L1, up arrow, to where the column header is highlight it and press clear. And then down arrow, and you'll see that the list is cleared out. Let's do the same thing for list L2. Alright, going back to list L1, we're going to type in the atmospheric pressures from the data set. Starting off with 760, enter 740, enter 725, enter 700, enter 650, 630, 600, 580, and 550. And then we're going to go over to list L2 and put in the corresponding heights. Starting off with 0, corresponding with an atmospheric pressure of 760, and then the next one is 0.184, enter, and then 0.328, 0.565. Oops, excuse me. I made a mistake here. Go back into our editor. We need to do 0.328, enter, and then 0.565. 1.079, 1.291, 1.634, 1.862, and 2.235. All right. Now, before we go any further, I'm going to go ahead and go in the equation editor. I'm going to clear out that function from the previous problem. And now I'm going to go into the stat plot and make sure that's turned on for number 1. Now for this one, we are going to have the pressure as the independent variable. So that's going to be an L1, and then L2 is the height. Alright, so let's go to our window, and our pressure is going to vary between 550 and 760. So why don't we go from 500 to, I don't know, 800 maybe, by 50s. And then for the heights, go from 0 to 2.235, so we can go from 0 to 2.3. And go by maybe 0.1s. Or maybe 0.2s. Alright, so go ahead and graph it. That's the plot that I have. Now we're going to go ahead and quit, and let's do a regression now. Go into your stat plot, calculate, and you have to scroll down using your down arrow button, and let's hit option 9, which is ln reg, as in you doing a regression with the natural logarithm, and hit enter. And the calculator is giving us this equation of the form y equals a plus b times natural log of x, where a is 45.78632063 and b is negative 0.6902524298. Okay. Alright, so there we go. Now we've done, we need to draw the logarithmic function found in part B. So what we could do, is we could type this equation into our graphing calculator, but I'm going to show you a little trick. Whenever you do a regression, so let's go ahead and redo our regression. Whenever you do a regression and you want the equation to be pasted into your equation editor for one of the y variables, so here's what you could do. You go to variables, see this button right here, variables, then right arrow over to y variables and select function, which is the first function, enter, and select which one of these y variables. Let's go ahead and use y sub 1. And then go ahead and hit enter. So you see the regression that's already been done, but go ahead and select the equation editor, go into it, and you notice that the function's already been pasted into it. So that's a huge time saver in my book. So there we go. And then hit graph. And there we've drawn the graph of the regression equation on top of the data set. Okay? And notice it's a good fit. The curve goes right through the data points. We're going to use the function to predict the height of the weather balloon if the atmospheric pressure is 560. And remember, the pressure, that's the x variable here. And so we will evaluate it at 560. Now we could go ahead and plug in 560 for x in the equation. But let's do our little trick here. Go back to your table menu. Let's, well, we've already got our table setup done. Go into your table menu. And let's go ahead and plug in 650 for x. Is it 650? Or excuse me, it's 560. When the pressure is 560, so the predicted height would be 2.1 kilometers. Okay. So we've already done all this. And we found the prediction that the height corresponding to 560 millimeters of mercury is going to be approximately 2.108 kilometers. Okay, now lastly our logistic model. Alright, so I'm not going to show you the keystrokes on the calculator. I'm just going to briefly go through this. And uh, so if you repeat the steps that we just did by inputting the data, but this time you're going to, when you do regression, you'll use the logistic regression. So you create the scatter plot for the data, do the logistic regression to get the equation in this form right here. Remember our good old friend, the logistic equation? You're going to get A, B, and C, where A is the multiplier for the exponential, and B is the multiplier for the variable x, and C is the numerator for the fraction. We always think about C in this logistic equation, the numerator, as the carrying capacity, by the way. You go ahead and plot the functions graph on top of the data set, like I showed you guys how to do. You can go ahead and write your logistic equation, like you see here, by just snatching off A, B, and C from the regression screen. And then you can answer the question, what's the carrying capacity? It's about 663, whatever C is here. Now, in the context of the problem, we're talking about number, or it's the yeast biomass. Now, if we're talking about an integer number of individuals, like in cells or monkeys or snails or whatever, you're going to want to make sure that you answer the question as far as the carrying capacity as an integer. Here, biomass is not necessarily an integer, but we round at C to the nearest tenth position, to one decimal place, so that answer was 663 as to the carrying capacity. To answer part E, what's the predicted amount of yeast biomass at T equals 19 hours? Well, replace x by 19. X is going to be the time variable. And evaluate this function at T equals 19. And that works out to be 661.5. Okay? So there you go. There's a real quick lecture on doing regression for exponential, logarithm, and logistic functions. Okay? So that is it. The last of the material that we're going to cover this semester. Homework is already posted, and later this week we will start talking about the final exam. Okay, folks, so that's it. We'll talk with you next time.